So here we have a system, x plus y plus z equals 1 and y minus z equals 0. So let's make some observations about this system. First of all, notice the following, right? Only two equations, but three variables. That tells us something important already. So what does that tell us? For example, you can solve bottom for y. When you do that, you would know that y is equal to z this way. Just add z to the right side. Now, since y and z are equal, at step 3, just replace, say, y with z in equation 1. Let's do that. So when we do that, we will have the following: x plus z for y plus z equals 1. So look what happens. You're going to have x plus 2z equals 1, which means x equals to 1 minus 2z. What is all of this telling us? Well, let's see. First of all, it's telling us that z can be anything. What does that mean? It means this: if z is 1, then y is equal to the following. Because y and z are equal, then y is also 1. It just happens that y and z are equal. Like I could have written here 2y minus z equals 0, you see? Or I could have written 1/2 of y minus 3z equals 0. So I just kept y minus z for the sake of simplicity. So when z is 1, y is 1, but that means that x is equal to 1 minus 2 times the value of z that I just made up. I made that up. Nothing special about z equals 1. So you end up here with 1 minus 2, which is negative 1. So what this is saying in this particular case is the following: that in this case we have the point, in other words, that looks like this. That makes the system true. The point is negative 1, comma 1, comma positive 1. That's one point. But what does it mean to say z can be anything? It means if I felt like it, I could say z equal to 0 right there. Why not? You see, there's nothing special about z equals 1. So I can say y is then equal to also 0 because z and y are equal, which means lastly that x would be equal to 1 minus 2 times 0, which is just 1. So in this case, the point that makes the system true would be the point that looks like the following: 1, comma 0, comma 0. Notice that we have 2 points. I could just continue pretty much forever, right, to choose the next value of z. Z equals 4, z equals 5, z equals 900, right? Z equals Bob, whatever, right? Z equals, z sub 0, just some value of z. Each choice of z will generate a new value of y and a corresponding value of x, which means what you end up with is infinitely many points. Now, a standard way to interpret an equation like this of a linear type with x, y, and z is as a plane, right? That y minus z in this context you can also imagine as a plane. And these points that you see here, like these 2 points alone, for example, what they represent are the following: points on line of intersection, okay, between the planes. That's what those points represent. So what does that mean? Give me 1 second here. I need to grab a couple sheets of paper. Okay, so let's look at a couple sheets of paper now. It's bigger. If you grab a couple sheets of paper like this, right, this is one plane, this is another plane. What you can do is kind of slide them together, and when you do that, you see where they meet, they form a line right there where the 2 planes meet. So like x plus y plus z is one plane, y minus z equals 0 is another plane, and they meet in a line. And the points negative 1, 1, 1, 1, 0, 0 kind of are points that belong to this line of intersection between the planes. But as you can see, this line, a line is made of infinitely many points, so that means those 2 points are just that, 2 points. There are infinitely many other points. So in other words, you have infinitely many solutions. So the negative 1, 1, and then 1, 0, 0 are just a couple of those solutions. You can check them in a system, they work, right? Like negative 1 plus 1 is 0, with z being equal to 1, it's equal to 1. Check the other one, y minus z. So it's 1 minus 1 is 0. That works, you see. Check the other point. 1 plus 0 is equal to 1, true. Y minus 0, well, 0 minus 0 is equal to 0. It works, you see. Leave a like if it's helpful.